Welcome to this explainer. All right, let's just jump straight into a seriously fascinating corner of chemistry today. We're talking about the D-block elements. You know them as the precious metals and the absolute industrial giants of our world. But here's the best part. These elements, they absolutely love to break the periodic rules. They're essentially the rebels of the periodic table. And understanding their rebellion is exactly how we unlock the secrets to some of the most important materials on Earth.
So let's quickly map out our journey. We'll kick things off with an introduction to the D block, move right into their totally unique trends, explore unpaired electrons, and see how they create colors and magnetism. Then we'll wrap up with alloys, catalysts, and the real-world creation of potassium permanganate. Let's get into it.
Okay, Section 1, Intro to the D block, also known as the transition metals. Think of them as the middle children of the periodic table. They sit right there between the S and P blocks, which is exactly where their final electron drops perfectly into a d orbital. Because they sit in the middle, they transition us from S to P, hence the name transition metals. But wait, I want to pose a foundational question to you here. Are all D block elements actually true transition metals? Well, that brings us to our very first major exception. To be considered a true transition metal by the rulebook, an element needs to have an incompletely filled d orbital. But take a look at zinc, cadmium, and mercury. Their d orbitals are fully filled with 10 electrons. They're perfectly stable. So because their d orbitals are maxed out, they are technically d block elements, but they are absolutely not true transition metals. Now, to really master these elements, it helps immensely to know the first series by heart. I want to anchor you with a fun little memory trick so you can effortlessly follow along with us. Just remember this: science teacher Vanny core manganese pier cobalt nickel copper zinc, right? That gives you scandium, titanium, vanadium, chromium, manganese, iron, which covers the Fe part, and then cobalt, nickel, copper, and zinc. Definitely keep that sequence in your back pocket. Moving on to Section 2. Trends and exceptions, breaking the rules. Let's see what actually happens to their physical properties when reality starts clashing with the standard textbook. When we talk about atomic size, things get really weird really fast. To understand why, you have to look at the incredible tug-of-war happening inside the atom. You have the effective nuclear charge, or Z effective, pulling outer electrons inward. But this is opposed by the screening effect of inner electrons blocking that pull. It's kind of like hanging transparent curtains between you and a chalkboard. The more curtains you add, the harder it is to see the board, right? Normally, as we go left to right across a period, atoms just get smaller. Simple enough. But the D block trend is wild. Starting from scandium, the size does decrease as the pull of Z effective dominates. But right around iron, cobalt, and nickel, it completely levels off. That's because the screening effect of the electrons perfectly balances out the nuclear pull. And then, surprisingly, at the very end of the series, with copper and zinc, the atomic size actually increases. The screening effect of all those extra electrons just takes over and pushes the outer shell away. No way, right? And it gets better. If you look vertically down the periodic table, you hit another massive exception. The general rule is that as you go down a group, atoms get bigger because you're adding more shells. But when you move from the second D block series to the third, the atoms are almost the exact same size. Why? It's all because of lanthanide contraction. The 4f orbital electrons are just terrible at shielding. This poor shielding allows the nucleus to pull the outer electrons in super tight, so the second and third series end up being the exact same size, completely throwing the standard rule out the window.
All right, Section 3, Unpaired Electrons, the true superheroes. We've seen how they break the rules of size, so let's meet the real driver behind all this crazy behavior.
It all comes down to unpaired electrons. They dictate how much energy is needed to strip an electron away, which is known as ionization enthalpy. Atoms desperately want to be stable, right? And a half-filled d5 orbital or a fully filled d10 orbital is literally the holy grail of chemical stability. These highly stable elements will flat out refuse to give up electrons if it ruins that balance. This leads to massive, totally unexpected spikes in the energy required to remove an electron for elements like chromium, copper, and manganese. These unpaired electrons also give them the ability to have variable oxidation states. Because the energy gap between their outermost s orbital and inner d orbital is incredibly small, they can easily share electrons from both. Take elements on the edges, like scandium and zinc. They only have one stable oxidation state, but the elements right in the middle, like manganese, they have up to 6 different oxidation states, from +2 all the way to +7. They are absolute chemical acrobats. Which brings us to Section 4, Colors and Magnetism. Superpowers of the D-block. Let's see how these unpaired electrons give these metals their most famous traits.
So, the vibrant colors of transition metal ions actually come from something called a d-d transition. Inside the atom, the d orbital splits into two slightly different energy levels. Think of an unpaired electron like someone who just found a $100 bill. They absorb that energy, jump up with excitement to a higher state. But quickly, they realize it's highly unstable up there, so they fall right back down to their ground state. And as that electron drops, it releases that excess energy as beautiful, visible light.
This brilliantly illustrates the core rule. Let's compare scandium 3+ and titanium 3+. Scandium 3+ has 0 electrons in its d orbital. No unpaired electrons means no jumping, which means absolutely no color. It is completely colorless. But titanium 3+, it has exactly 1 unpaired electron. That single electron absorbs energy, jumps, falls, and emits a vibrant purple color. So the whole shebang really just comes down to the unpaired electron.
Section 5. Alloys and catalysts. Industrial workhorses. Beyond just looking pretty in a test tube, these unique atomic structures are literally what built our modern world.
Because transition metals have very similar atomic sizes, you can melt them down and easily mix them together to form alloys. These alloys are much harder and have way higher melting points than pure metals. And here's a totally surprising fact for you. German silver contains absolutely 0 actual silver. Yeah, none. It's just a clever, shiny blend of copper, nickel, and zinc.
On top of that, these metals are master catalysts. A catalyst speeds up a chemical reaction without being consumed itself. Because D-block elements have those variable oxidation states we talked about earlier, they're perfect for the job. You can think of a metal like iron acting as a chemical middleman. It speeds up a reaction by temporarily bonding with different reactants to form intermediate complexes, but then it sneaks away completely unchanged at the very end.
They also form what are called interstitial compounds. Imagine a metal's crystal lattice structure is like a tightly packed box of oranges. Even though it's packed tight, there are still tiny empty spaces between the fruit. Well, tiny atoms like carbon, nitrogen, or hydrogen can get trapped inside those gaps. And why does this matter? Because trapping these tiny atoms creates compounds that are incredibly hard, chemically inert, and have melting points even higher than pure metals.
Finally, Section 6. Making KMnO4, potassium permanganate. Let's ground all this fantastic theory in a real-world application.
In a general lab setting, making it is a highly logical two-step journey. First, you take raw pyrolusite ore, which is MnO2, and react it with potassium hydroxide and oxygen. This oxidation step creates a dark green intermediate called potassium manganate. Then, you put that green solution through an acidic disproportionation reaction, and boom, you get the famous dark purple potassium permanganate.
Now you might be wondering, what exactly is disproportionation? Let me point out the fascinating chemical magic happening here. It's a unique reaction where the exact same element acts against itself. The manganese in that green intermediate simultaneously oxidizes to a +7 state and reduces to a +4 state in the exact same reaction mixture to yield our final purple product.
But if you're running a massive industrial factory, you want to be as efficient as possible. The first step remains exactly the same, making that dark green potassium manganate. But instead of relying on chemical disproportionation, massive factories skip that entirely. They use electrolytic oxidation. They just run electricity right through the mixture to force the oxidation all the way to that final purple KMnO4 product rapidly and efficiently.
So, from atomic sizes that shrink and expand unpredictably to gorgeous colors born from leaping electrons, the D-block is just full of surprises. I want to leave you with this final thought to ponder today. If the most important industrially useful metals in our world continuously break the standard rules of the periodic table, are they really just exceptions? Or are they actually showing us the true, beautifully complex reality of chemistry? Thanks so much for joining me on this explainer, and keep questioning the rules.